now a design strategy for H-plane sectoral horns. The equations I'm going to show you are obtained by curve fitting to the preceding results, not specifically to the results I showed just now, but rather to data which was developed using the techniques I'm talking about. So if you work through enough cases, you can do a fit to all the possible outcomes. That's known as empirical modeling. So an empirically derived expression for the optimal value of A, call that A sub opt, turns out to be the square root of 3 times lambda times R1. So for example, one way to go would be to choose the largest value of R1 that you can accommodate, that is the longest horn that you're willing to put up with, and then you know that the directivity is optimized by choosing A to be this value, right? And I should point out, this is really an approximation, and it's, again, obtained by empirical analysis. In any event, the half-power beam width in the appropriate plane, in this case, I really mean the H-plane, will be 78 degrees times lambda divided by A sub opt, assuming you choose that dimension. The directivity is hard to estimate accurately. That's something that's better to compute directly. So once you've designed a horn, you've selected R1, you selected A opt, you probably ought to do the numerical integration to get the directivity, although you could also get the half-power beam width, and if it's narrow enough, you could use one of the half-power beam width to directivity approximations, but again, this is usually better to compute directly. And then, of course, gain is about the same as directivity if the waveguide portion is properly fed. In other words, if you have a lossy waveguide or a lossy feed in the waveguide, then obviously the gain is not going to be equal to the directivity. It'll be somewhat less. Now what I'd like to do is demonstrate the accuracy of this particular set of equations, this particular empirical approach to designing these horns. So here what I'm showing are directivity curves for H-plane sectoral horns, which all have B equal 1 lambda. And then each curve corresponds to a different length of horn from 6 to 15 wavelengths. And then again, as a function of the opening of the aperture in the H-plane. And this result I've already shown. But now what I can do is see how well the empirical expressions correspond to what I calculate the long way. So, for example, the optimal value of the value A for R1 equals 15 wavelengths is 6.9. Our equations give us 6.7, so that's a pretty good guess. The half-power beam width is found to be 11.6 degrees. Our expressions give us 11.6 degrees. So you can see they're quite accurate. Similarly, for a horn which is 10 wavelengths, the actual optimum value of A is 5.7 wavelengths. We get 5.5 wavelengths from our equations. Half-power beam width is actually 14.1 degrees. Our equations give us 14.2 degrees. And then finally for R1 equals 6 wavelengths, the optimal value of A is 4.4 wavelengths. Our equations give us 4.2 wavelengths. Half-power beam width, 18.2 degrees in the H-plane. We get from our equations 18.6 degrees in the H-plane. So these design equations are quite safe to use in this regime of possible values. Concluding remarks. Just about horns in general. Horns are useful in applications where intermediate levels of directivity, and by that I mean maybe from 6 dB to 20 dB, are required. So certainly for dishes, horns find many applications, but also in arrays. You can have arrays of horns, and selected other applications, horns emerge. Again, when you need this kind of directivity that's perhaps greater than what you could reliably get from a patch, but less than a typical dish or a yagi, which would be much larger structures. The key idea in a horn is to increase aperture without disrupting phase uniformity too much. So again, we saw this trade-off. You can make the aperture an optimal size. If it's too small, you lose directivity because you've lost aperture. Make it too big, you lose directivity because of phase cancellation in the aperture. The H-plane sectoral horn is just one of many types of horns. This principle applies to basically all kinds of horn designs. H-plane sectoral horn is just one example. I should point out that closely related are the E-plane sectoral horn and the pyramidal horn. In this lecture, we focused on analytical methods and empirical approximations to those results, that is, the results you can get from relatively simple analysis. But it's also possible, and it's reasonable, to use full-wave numerical electromagnetic methods, such as finite difference time domain, such as the moment method. Those particular techniques, though, are most useful in confirming the performance of a candidate design. And the reason is because basically you enter a design and it gives back a result. It really doesn't tell you much about what you have to do to vary the parameters to get the design that you actually want. For that, it's useful to have simple types of expressions that tell you something about the relationship between the parameters. And so design procedures like what I've demonstrated here are a useful way to come up with a candidate design which can then be refined using a full-wave solver kind of approach. This concludes this lecture on the H-plane sectoral horn.